Hi everyone, and welcome to the end of activity 23. Today we are going to talk about verifying and solving with our multiple angle identities. So we've talked a little bit about our verifying identities in some previous lessons, and today we're going to keep working with that. So notice in this first one, we have a sum formula here. We are adding with a cosine here. So we're going to make our goal this right-hand side to get that negative sine theta as our final answer. So we want to think about kind of our x and our y that we are plugging in. Cosine of x times cosine of y, so aka cosine theta times cosine pi over 2. Remember with cosine, if it's a plus inside there, it's a minus here. Sine theta times the sine of pi over 2, again, sine of x times sine of y, which are just theta and pi over 2. Well, from the unit circle, we know that the cosine at pi over 2, aka 90 degrees, is 0. And we know that the sine at pi over 2 is 1. So cosine times 0 just becomes 0. And then this will be negative sine times 1, which is just negative sine. So we get that goal answer from our beginning. In our next one, we have another sum formula, this time with a tangent. And again, plugging in x and y, we would have tangent of theta plus tangent of pi, tan x plus tan y, and again, y is pi this time, all over 1 minus tangent of x, which is tangent theta, times the tangent of y, which again is tangent of pi. Now, the tangent of pi is actually going to be 0, because think about at pi, we are at negative 1 comma 0. 0 divided by negative 1 is 0. So anywhere we see tangent of pi, we need to plug in a 0. So we would have tangent of theta plus 0, and then 1 minus tangent of theta times 0. Tangent times 0 cancels out basically because it's just 0. 1 minus 0 is just 1. On the top, tangent plus 0 just is 0. Tangent divided by 1 is just tangent, which is what we wanted it to simplify to be. All right, for number 3, you are going to verify yourself. Remember, you're plugging in for x and y, your theta and 180. All right, number 4. Okay, we are verifying, this time we are going to verify using our double angle formulas, right? So in this case, cosine 2x, we have a couple options, right? Now notice our final answer involves cosine squared and a cosecant. So chances are we have a couple things we could substitute in, but what I'm going to substitute in for this cosine of 2x is the 2 cosine squared x minus 1, because now at least everything is in terms of cosine, which kind of based off our final answer is something we want to look for. We have 1 minus 1, so that becomes 0. And then we can rewrite, officially this looks like 2 cosine squared, and that sign is in our denominator, right? Well, we can rewrite that as a cosecant in our numerator, right? Move it up to the top using the reciprocal identity. So we get that final answer of 2 cosine squared x times cosecant of x. On our last example here, I'm actually going to make the left-hand side my goal this time. And again, I'm given a cosine of 2x. Notice I have kind of a cotangent happening here. So again, it may or may not be able to do a ton with that, but I think I'm just going to start again by plugging in the 2 cosine squared x minus 1 for that first piece, plus cosecant squared x, because I noticed that my final answer here wanted a cosine squared. So maybe getting everything at least with the cosine over there is helpful. Now, what we notice is if we rewrite this a little bit different order, right? If we put that cosecant squared first minus 1, this is actually a Pythagorean identity, right? We can substitute in cotangent squared x for that, and we are left with our final answer, right? Cotangent squared x plus 2 times cosine squared x, which was our goal. Now for solving, same kind of principles as before, just again, we have a couple different formulas that we can plug in instead. So notice this is not a cosine squared, it's a cosine 2 theta. So again, to keep everything in terms of the cosine squareds, what I'm going to do is I'm going to replace this with 2 cosine squared theta minus 1, and then we have plus 10 cosine squared, and then we have minus 8, right? So I have 2 cosine squared plus 10 cosine squared. I have a total of 12 cosine squareds. And then negative 1 minus 8 more is negative 9. So I have everything just with cosine squared here. So what I can do is I can add over the 9, and then I can divide by the 12 so that I get where is cosine squared equal to, if we simplify this, 3 over 4, right? Both those are divisible by 3 after we have that 9 over 12. And a reminder, and when we square root, okay, you want plus or minus. So we're looking where is cosine equal to the square root of 3 over the square root of 4. Well, the square root of 4 is 2. And then don't forget that plus or minus. We're really looking for where is this equal to positive or negative square root of 3 over 2 in radians, since we want 0 to 2 pi. So that's going to happen in all 4 of our quadrants at pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. In our next example, I have sine of 2 theta this time. So I'm going to have cosine of theta minus, and again, I'm going to be careful. I'm going to use parentheses just to double check, 2 sine theta times cosine theta, right? Now, in this case, these are being multiplied, so it's not really that big of a deal, but just in case I have to distribute, if I had addition or subtraction inside the parentheses, I want to make sure I have that. And again, this all currently equals 0. Now, what we notice is the cosines both are in each piece, so we have a GCF of cosine that we can actually officially take out. And if you divide both pieces by that cosine, cosine divided by cosine is 1, and then we divide out that cosine, but we still have a 2 sine theta. So officially we have 2 things we need to set equal to 0 this time, cosine and 1 minus 2 sine. Both of those get set equal to 0. So cosine is going to be 0 in 2 spots at pi over 2 and 3 pi over 2. And then if we add and divide, we end up getting where is sine equal to positive 1/2. That's going to happen in quadrants 1 and 2 at pi over 6 and 5 pi over 6. So we end up with 4 answers this time. Pi over 2 and 3 pi over 2 from the cosine equaling 0, pi over 6 and 5 pi over 6 from the sine equaling 1/2. All right, our last one we are looking at is another cosine of 2 theta. So again, we want to make a decision. Now in this case, I already have a cosine. So again, it's going to be to my advantage to change this cosine 2 theta to be 2 cosine squared minus 1, because I already have a cosine here. So now everything is in terms of cosine, at least the same trig there, right? And if we combine like terms, we have 2 cosine squared minus 3 cosine, and then the negative 1 but plus 2 would be positive 1. So notice we have a cosine squared, a cosine, and a constant. This is basically going to turn into some x solving, right? We have 2 and 1, so what multiplies to be 2? That adds to be negative 3. Well, negative 2 and negative 1 multiply to be 2, but add to be 3. So think about this as like we're saying 2x squared minus 3x, but we're going to divide that up to minus 2x minus 1x from these pieces in the middle there, and then plus 1. And again, we have to do that because of this leading coefficient of 2. So next thing we are going to do, take out a GCF. We have a 2x we can take out of the first part, a -1 out of the second. So we end up with 2x minus 1, and x minus 1 is our two factors, aka where does 2 cosine x minus 1 equal 0? Where does cosine x minus 1 equal 0? Because again, we're speaking in terms of cosine. So cosine is going to be 1/2 in our first and fourth quadrant at pi over 3, and in quadrant 4 at 5 pi over 3. Cosine is going to be positive 1 over at 0. Again, you don't include 2 pi because it's got a parenthesis up in our instructions, not a bracket. So that's why we would include 0, but not necessarily 2 pi. All right, thanks everyone for watching. We'll definitely be working more with each of these types in class.